Today we're going to look at the American High School Math Exam, abbreviated as Ahsme, from the year 1960. This is the precursor to the AMC, or the American Mathematics Competition, that's published by the Mathematical Association of America. The AMC, in its current incarnation, consists of 25 questions to be completed in 75 minutes. The Ahsme from 1960 was divided into three parts. Part 1 consisted of 20 questions, and parts 2 and 3 had 10 questions each. But I've been unable to find any information about how much time was allowed for students to complete this exam. What hasn't changed between 1960 and now is it's always been multiple choice with 5 answer choices to choose from. I found a lot of my information about this older AMC from the first contest problem book published by the MAA. You can also find historical AMCs at the Art of Problem Solving website. According to this book, in 1960, there were at least 150,000 students taking the Ahsme. Before COVID, it seems like we may have had 100,000 or so students taking the AMC, and after COVID, that number dropped to 50,000. I'm not 100% sure of these numbers. If you have different information about the number of students currently taking the AMC, please leave them in the comments. According to the book, it looks like part 1 had easier questions, and parts 2 and 3 were more challenging. So let's take a look at the final 5. The first problem in the 1960 Ahsme final 5 is problem number 36. We're going to use this formula for the sum of terms in an arithmetic sequence. It's the first term plus the last term, take the average, and multiply by n, the number of terms. So we'll write S1, S2, and S3 in terms of this formula. S1 consists of n terms. Our first term is a, and our last term is a plus n minus 1 times d, and we'll simplify the numerator a bit. S2 has 2 times n terms. The first term is a, the last term is a plus 2n minus 1 times d. Divide this by 2 and simplify the numerator. And similarly for S3. Their variable r is S3 minus S2 minus S1. So let's substitute, and we'll factor out 1/2 from all 3 terms. Now we'll expand and combine like terms and see which variables disappear. This is 6an, this is 4an, and minus 2an. These an terms all disappear, and we'll expand these remaining 3 terms. When we factor out d from all of this, we have this 9n squared and minus 5n squared, leaving us with 4n squared. This is minus 3n, and then we have plus 3n. So r is equal to 2n squared d. Returning to our problem statement, we see that r only depends on d and n, so our answer is option B. Let's go on to the next final 5, problem number 37. We'll start by drawing a triangle and labeling the lengths of the base and the height. We have a rectangle inscribed inside that shares one side with the side of the triangle, and the height of this rectangle is x. Drawing a perpendicular from the vertex of the triangle to the top of the rectangle, this distance is h minus x. Let's call the width of our rectangle w. If we label this small triangle up top here triangle ABC, then we see that this triangle is similar to triangle ADE. So we can compare the bases and the altitudes of these two triangles. The base of our small triangle is the width of this rectangle, or w, and the height is h minus x. The base of our large triangle is b, and the height is h. So we'll solve for w. We're asked to find the area of the rectangle. Here the base of the rectangle is w, and the height is x. So we'll substitute, and we'll look for this expression in our answer choices, and we see that this is equivalent to answer choice A. So let's go on to problem 38. They give us some expressions in terms of the angle measures, so let's do some angle chasing. We're given that triangle ABC is isosceles, which means the base angles are congruent. I'll label those as x. We're also given that the central triangle DEF is equilateral, so we have 60-degree angles at each vertex. Let's find an expression for this angle up top, angle BDF. It's supplementary with this angle in the equilateral triangle and angle B over here. So I'll say this is 180 degrees minus 60 degrees minus b. Similarly, down here for angle EFC, because it's supplementary with these two other angles, I'm going to write that as 180 minus 60 minus a, or 120 minus a. If we compare triangles BDF and EFC, both of them have an angle sum of 180 degrees. If we subtract x from both of them, then the sum of the other two angles will be equal. So from triangle BDF, we have 120 minus b plus a, and for EFC, we have 120 minus a plus c. Let's see if we can get an equation that looks like one of the answer choices. We subtract 120 from both sides. We'll add a to both sides, leaving us with 2a, and then b plus c on the other side. Solving for a, we get b plus c over 2 and hope it's one of the answer choices. We see that it's answer choice D. Let's go to the next final 5, problem number 39. Let's multiply by the denominators to get rid of the fractions and expand the left-hand side. Subtract ab. We can read this as a quadratic in a, so we'll solve this using the quadratic formula. Our answer choices offer combinations of real or rational solutions. So let's see what happens when b is a real number. Nothing cancels out this I here, so a is not going to be a real number. If b is not a real number, we still don't know if that I is going to be canceled. So we don't know then if a is a real number. Let's look at our answer choices. We know that they both can't be real, so we can eliminate b. We don't know if they're both not real. Depending on the value of b, a could be real, so we'll eliminate c. We can have one real and one not real, or we could have both of them are not real, so we can eliminate d. This last one, e, is the hardest to parse, so it seems to me like it reads as either one real and one not real, or both not real. And I think that's what we have in our solution. Since all rational numbers are real, we can also eliminate option A. So our answer is E. Let's go on to the final problem, number 40. Let's draw our right triangle and one of our trisectors. So this angle down here is 30 degrees, and this is 60. So we think about creating a 30, 60, 90 triangle here to the right. Let's call this segment PQ, and it's perpendicular to AC. Let's let the distance from C to Q be equal to X, and since this is a 30, 60, 90 triangle, PQ is X root 3 and PC is 2X. We want to find this length PC, and we notice that triangle PQA is similar to the 3, 4, 5 triangle BCA. If CQ is X, then QA on this triangle is 4 minus X. We'll set up the ratio for the corresponding sides. The two legs are in ratio of 3 to 4. We'll multiply by the denominators and solve for X. And we'll rationalize the denominator. We want to find 2X, which is 32 root 3 minus 24 over 13. And we see this is answer choice A. If you have any questions about this or any other math contest problems, please leave them in the comments.